favorite day class? My favorite. Like kid. Let you tell. You're everyone's favorite. Hopefully I won't have to talk too long to you guys today. There's a few little pieces we didn't finish yesterday. I want to pick up some terms you didn't get defined. Static electricity, electroscope, conductor, and insulator. Those are the words you have left to define today. So look for those as we go through this. I mentioned that we're going to be addressing these three questions. What's electricity? What's magnetism? And how are they related? And that with the what is electricity question, what is electricity? Everybody.
It's flow of electrons through a circuit.
Excellent. And I'm going to ask that every day. And you're going to be so sick of hearing it by the end of this unit.
Then we're going to understand it.
But you'll have it. Yeah, well, at least you'll be able to spout it back. You may not understand it, but hopefully you will understand it. We're going to cover two different kinds of electricity. And you can write down the definition, that's fine, but what I really hope is that you'll have a true understanding in your gut. You'll understand the difference. Two basic kinds of electricity. We have electricity that we get from a wall outlet, electricity that we get from a battery. The electricity that we really use is the kind that keeps on flowing. Just like you saw the little animation with the light bulb. It flows through the light bulb to the battery and back again. It just keeps flowing, okay? And that type of electricity is often referred to as current electricity. In fact, the definition you wrote for electricity is really the definition for current electricity. In fact, I'd like you to write the word current before that. Current electricity. And I don't mean current like up to date, it's very modern. I mean current like current in the ocean, how it just keeps flowing and it's this pushing force that keeps going. So if we're going to power the radio on that island, remember that deserted island we crashed on, we're going to need a regular flow, not just a quick little burst. We're not going to be able to power the radio. We're not going to be able to power the radio from, say, a bolt of lightning. Because the bolt of lightning goes boom, and it's over with. Okay? It doesn't keep the flow going. When you scuff your feet on the carpet and you touch someone and you shock them, it's boom, and it's all over with. That kind of electricity is referred to as static electricity. And when we get static electricity, like scuffing your feet on the carpet, what we are actually doing is pulling what off the carpet? Electrons. And they're building up on the outside of our body. We say that that person is charged. When you're charged, that means you have a buildup of electrons. Now, theoretically, if I could build up protons on your body, extra protons, you'd also be charged. But usually it's electrons. Why? Why electrons and not protons? Why are they the things that get knocked off and not the protons?
Because they're outside the nucleus.
Good. They're outside the nucleus. That's one reason. What else? Okay, there's, well, not necessarily more. They're always moving. What else? What about their mass and size? The mass is very, very small compared to a proton. If this were a proton, an electron would be a tiny little speck. They're very small. So every atom, the atoms of your wood desk there, of your arm, of every substance, has electrons spinning around the outside. And if we could get those electrons to move and flow in, say, a circuit, we have electricity. Get it? In static electricity, the electrons don't flow, at least not most of the time. They just sit there. That's what makes it static. The word static means not moving. For a star, who can tell me the term that means moving?
Alternating?
No. It's a good guess, though. We'll get to that word later on. You know, in PE, we do different kinds of stretches, and some people do the wrong kind of stretches. The right kind of stretch is you reach down there and you hold the position. We call that static stretching. The wrong kind of stretching is where you bounce up and down trying to touch your toes, and they call that a whole different kind of stretching. They actually have a whole branch of forensic science named after this term. No? Excellent. Good job. Ballistic. So ballistic means moving. So like when you're studying ballistics, you're studying things that move, bullets. And you know, the little lines that the gun leaves on the bullets. So that's a good term to know. Not one we have here in electricity, but ballistic means moving. Okay, so static electricity, the charges build up on the outside of the object. And then they are transferred. So there's your definition for static. Static electricity. If you didn't get it down, I'll read it out for you here again. Static electricity is the buildup of electrons on an object. The word static means not moving. And when we build up those charges, we shoved our feet on the carpet, we got extra electrons, they don't move because we haven't given them a good path. When you talk about static electricity, you're always looking at things that don't carry electricity well. Think about it. What's the last time a static charge built up on a piece of metal? It may go to the piece of metal, but it never builds up on it. If I get a static charge, it's always things like cloth, fur, plastic, styrofoam, things that don't act well for carrying electricity. Okay? Those are things we call good insulators. An insulator resists the flow of electrons. An insulator is a material that resists the flow of electrons. A material that resists the flow of electrons. So what you should imagine for an insulator is the atoms of this plastic, a good insulator, or of the fur. The electrons that are spinning around the outside, they hang on tight. Those bees don't want to leave that beehive. As opposed to materials like metal, or what do we make wires out of? Copper, another metal. Those are examples of good conductors. A material that gives up its electrons easily. A material that gives up its electrons easily. Those electrons, even though it's something hard, you wouldn't think, well, that doesn't make sense. Well, it does. Those electrons will move easily. And therefore, we can get electricity to flow through things that are made of metal, like copper. But things that are made of insulators, like plastic, glass is a good insulator. Air is an excellent insulator. Electricity doesn't typically, unless you have a ton of it, head up please, doesn't typically just jump through the air. It has to have a lot of energy in order to jump through the air. That's why I can go over here and get my hand real close to the outlet and don't have to worry about being shocked because I'm not actually touching it. It doesn't just jump through the air. Get it? Air doesn't give up its electrons easily. Neither does the fur, neither does the plastic. Now, we talked about electrons and some rules that they follow yesterday. And I told you that typically most objects have what charge? Neutral. No charge. That means they have an equal number of what and what? Protons and electrons. What doesn't get to vote in this whole thing? Neutrons. What two particles are located in the nucleus? Okay. So the protons and neutrons are in the middle. The neutrons don't get to vote. Most things have an equal number of electrons and protons. So no charge. So right now, the charge on this piece of fur is neutral. The charge on this rod is neutral. Okay? When I rub the fur onto the plastic rod, I happen to know that the electrons will come from the fur and go onto the rod. I'll be transferring them to the rod. That means the fur temporarily, let's make sure we act like we're in 8th grade, okay? The fur temporarily is what charge? You said positive, you're right, and that's good. Because, remember, it was neutral. What did I take away from it? Electrons, leaving it positive. Now, it won't stay positive for long, because now that it's just sitting here, it is exposed to other electrons. Where is it coming from? The air. The air is in contact with the fur. I know, again, you guys think that there's nothing here. There is something. There is atmosphere. There is air. There's oxygen. There's nitrogen. There's a whole bunch of different gases floating around. And all those gases are made of atoms. And all the atoms have electrons. And so if this needs some extra electrons, you can pull them right from the air. Okay? And so this then becomes neutral in a short period of time, because it'll get those electrons from the air. This guy that I rubbed with the fur, it became what charge? Negative, because I added extra electrons. and it will keep that charge for a little while. The reason the charge stays on the rod is because the rod is a good insulator. I couldn't do this experiment with a piece of metal, because the piece of metal, the electrons would want to flow through it. Metal is a good conductor, and they would flow through the metal, and then all the electrons would go into me, and I'd never be able to get the rod charged up. But because this is plastic, they want to just stay there. They don't have a good way of going. Now, they will eventually leave. It's hard for them to go into the air, but they will eventually find their way to a better place to go, a place that's less crowded, has fewer electrons. But I have this device here called an electroscope, one of your terms. And an electroscope is a device that's used to detect static charges. An electroscope is a device used to detect static charges. And basically what it consists of is this little ball and a rod that goes down and has two pieces of foil hanging from that rod. Okay? The two pieces of foil are called leaves, like leaves on a tree. And when they hang straight down, that shows me that there is no charge. I wouldn't use this to see if there's electricity in the outlet. That's a good way to blow myself up. Okay? I would use this to see if there's a buildup of charges someplace. So I'm going to charge the rod. That means I'm going to transfer electrons to it. And when I touch the electroscope, predict what's going to happen to the leaves. Going to rise. Okay, they're hanging from the top. They're going to separate. You're right. Because the electrons will flow down through the rod and go and coat each of those two leaves. And if I have a negative next to a negative, what do you know about like charges? They repel. And you can see that I'm making those move. Sealed inside that glass, there's no way to touch those, but the charges themselves are making the leaves move. As long as they move away from each other, I could show you that that has a charge. Now let's just imagine for a moment that I could move protons. I could take some protons and put the protons on there. What would the leaves do? Would they attract? Why would they separate? Exactly. It's always going to separate if there's a charge. Whether it's a positive or a negative charge, it doesn't matter. Because like charges repel. There's no way with this device that I can make those two leaves go together, because I'd have to make one positive and one negative, and I can't do that when they're hooked onto the same piece of metal. So again, an electroscope detects the presence of static charges. In static electricity, we say charge and discharge. I build up the charge and I discharge it. You step your feet on the carpet, you build up the charge, you touch the light switch, that spark jumps from your finger to the light switch, and you discharge. Get it? All right, so you should have, is that everything? All your terms defined. Let me talk a little bit more about conductor and insulator. And I really want to help you to visualize this. So I need some volunteers up here that don't mind a little violence. Okay, 1, 2, 3, 4. Come on up. We're going to have a little violence. Okay, I need you to imagine now for a moment that each of these people are electrons. Electrons on an atom. Okay? And you're spinning around the outside. It's like a little bead. Okay? And what you're going to do is you're going to influence the electron next to you, or the atom next to you. You're going to influence the one next to you, and so on. Spit out your gum, please. I noticed that you get to chew it everywhere else. I saw you in the office. You walking around all day long with gum in your mouth. No one seems to call you on it. Anyway, so when I showed you, remember the little animation I showed up here with the light bulb and the circuit and the little red dots? Remember that? That's kind of misleading. It makes you think that the electrons just kind of zip through the wire. Like, hey, just run right through the wire, go all the way through. That's not what happens. The electrons actually influence the next one. If I have a negative charge, I'm an electron, and she has a negative charge, and I get close, what's going to happen? Like charges repel. So if I hit her with some energy, boom, she's going to pass it on, and so on. You still with me? Because like charges repel. So really what happens in that wire of copper, let's make a wire here, little choo-choo train, hands on the shoulders of the person in front of you. Going that way, okay? What happens is Yeah, no. So what happens is whatever I put in here, I should get out there. If this is a good wire, let's say you guys are made of copper. I give a little shove here. Told you it was going to be violent. I knocked the pin right off. That's cool. Do it again. All right. So you guys need to listen. What kind of material you are? You are now a wire made of, what's something better than copper? Gold. Gold is a better conductor. Because the electrons on atoms of gold, those electrons, they move very easily in gold. The electrons move very easily. So whatever I put in here, I get out there. You all right there? I bring you back? Okay, look out. One more time. So that was a gold wire. Let's say that you guys are a wire made of, oh, I don't know, plastic. Solid plastic. Okay, I want you to behave accordingly. Good. What goes in is not what I get out. Because the electrons in plastic, they don't move easily. They want to stay on their atom. They don't give themselves up and move away easily. So we don't get the domino effect. Okay? Let's try another one. Aluminum. Should that have gone through? Yeah. Is aluminum a conductor? Yes, it is. Not as good as copper, but it is a pretty good conductor. Let's try again. Copper. There we go. Let's try again. See if you guys were paying attention. We'll make ourselves a wire out of air. Out of nitrogen and hydrogen and oxygen. Okay? A wire out of air isn't going to carry electricity well. But can you think of any situation where air actually does carry electricity? Lightning. Or how about every time you scuff your feet and you touch some metal thing that goes to the earth, and that spark comes off, and it's half an inch or an inch long, that blue spark, okay? That requires a lot of energy. Let's line up here again. More lightning. Okay, so in order to simulate lightning going through the air, I'm going to need to get a good running start here. I won't. You guys go sit. That's called lawsuit. That's what that's called. But you get the idea. Even something like air that's going to resist that flow. You get enough energy going, you can force lightning right through the air. We'll talk about how we change the air a little bit to make that happen in a few days, okay? But that's what we're doing. We're working with conductors or insulators. With static electricity, insulators are always involved because they don't give up the electricity well. It sits there and it doesn't move easily because it's a good insulator. It looks for a place to discharge. All right, one more little famous demo to show you. They always use with electricity. And basically all I have is just like a coat hanger, and this is just a little piece of styrofoam hanging from a thread. Good insulators, okay? So it can show me if it gets a static charge. They call this a pith ball, P-I-T-H. Pithy means, you know, really light and fluffy. You could use a little puff, a little wheat puff from your breakfast cereal to do the same thing. So anyway, this is going to show us how charges actually have an effect. And I have questions on the quiz here in a little bit. Tell me the charge on this piece of fur right now.
Neutral.
On this plastic rod.
Neutral.
On that pith ball.
Neutral.
Neutral. And when things are neutral, nothing remarkable happens. Ooh, nothing's happening. Whoop-de-doo, right? But as soon as we transfer charges, then we know the rule. Like charges, unlike charges, attract. Okay? So I'm going to rub the rod with the fur, and I'm going to transfer electrons from the fur to the rod, making the fur what charge temporarily? Positive. I took electrons away. It's positive. I made the rod negative. When I bring the rod close to the pith ball, predict what's going to happen. Is it going to be attracted, repelled, or do nothing?
Do nothing. Attract.
It's going to be attracted. What happens when you take a balloon and you rub it on your head and you bring it next to the wall? Is it attracted, repelled, or do nothing? Attracted. Because the electrons in that balloon want to go to the wall and into the earth. It wants to go to a bigger place, okay? And a better place. So, you're right, it's going to be attracted. Now, Which is bigger, the rod or the little pup there? The rod is bigger. Do you think I'm going to transfer all the electrons into that pith ball? No, they won't all fit. So what's the charge on the rod? Negative. What's the charge on the pith ball? Negative. What's going to happen when I bring this next to it? Everyone thinks that's some sort of trick. That is electricity. That is the the invisible electrons that you can't see, because you can't see electricity, but you can see the effects of it. That's electrons on the pith ball and electrons on the rod repelling one another. Okay? Now, I gave it the magic, and I can take it away. How would I get rid of these charges? This is already neutral. Got it from the air. How am I going to get rid of this charge? Shake it. Will that get rid of them? No, that didn't do it. What can I do? Better still, touch it to some metal that goes to the earth, like this water pole. I know this goes straight into the ground, and it'll just soak up and take those electrons off. I mean, I could rub it with my hand, and maybe some of the electrons will come off into my hand if it's a better place, but the metal is far better. Okay? Come over here and maybe get some of those electrons off the pith ball by handling it. And now I have grounded it, we say. That means I've given the electrons a place to go. What's the charge on this now? And on that? And nothing remarkable happens. Okay? You take away the charge. How many think they understand it? Great. Now, just so you're clear, I'm going to give you a little more detailed look at what's really going on here. Those are all the definitions you should have, by the way, so far. But here's a little electronic simulation of what I was doing. And I know these are really too small for you guys to see, but that's showing the rod has a bunch of electrons on the outside. It's negatively charged. We rubbed it with the fur. And here's the pith ball. It has what charge? Neutral. When I bring this near it, notice what's happening to the pith ball. It's hard to see, but this side of the ball is getting what charge? Positive. And this side is getting negative. And here's why that happens. The closer this gets, the negative charges in the wand are repelling the negative charges on this side of the ball. It's pushing them over that way. Why? Because like charges repel. So it pushed the electrons over to the other side of the pith ball. That's what makes this side positive. And that is why the two come together and stick. Because opposites attract. So once it gets up to it and I transfer electrons, boom, immediately it becomes charged so that the entire thing is negative. That entire ball is negative. And I can't bring that next to it. Like charges repel. If I want to get it back to the way it was, I just put my hand in there, touch that ball, and I ground it, and now I can have it be attracted again. You see? And this is what happens all the time in our world. Electrons aren't just staying put. They're going from one place to another. New beaches are being opened up, and they're going, ooh, better spot over there, let's go. And then another one opens up, and they move over here. So they're moving all over the place. Electricity makes the world go around, literally and figuratively. Okay? Any questions on that? All right. I need you to clear your desk of everything. All you need is a pen or a pencil. We're going to do a quick little review here. Who wants the spider? Thinks they know this stuff well? Okay? We'll see if we can get through all the questions without making a mistake. Question number 1. Name 3 forms of energy.
Electricity, magnetism, and chemical.
You got it. Ask it to someone else that thinks they know this stuff well. Okay? Second question. Electricity is the flow of what?
Electrons.
Got it. Pass it off. Okay? An object with 3 electrons and 5 protons has what charge?
Positive.
Positive what? 3 electrons and 5 protons.
Positive.
Good. So far so good. Pass it off. What was the charge in this experiment on the fur before I rubbed it with the rod? Neutral. 0. Pass it off. What was the charge on the rod before I rubbed it with the fur?
Neutral.
Pass it off. Oh, come on. You can do it. You were here right now. These are questions from right now. In fact, I've covered everything from yesterday right now. Okay, Nathan, what was the charge on the pith ball before I touched it?
Neutral.
Neutral. Pass it off. Okay, what was the charge on the fur after I rubbed it with the rod? So electrons went from the fur to the rod. What was the charge on the fur? Oh, pass it off. What was the charge on the fur? Positive. Pass it off. Okay, after rubbing the rod on the fur, what was the charge on the rod? Negative. Okay, what was the charge on the pith ball after I touched it with the rod? Negative. Pass it off. Almost done here. Come on, be brave. No, you already did one. Pass it to someone else. Okay. Opposite charges.
Opposites attract.
Attract. Spell attract for me. A-T-T-R-A-C-T. There's no K in attract. Okay? It's not attack, it's attract. Alike charges do what? No, not resist. Pass it off. Repel. Spell repel for me. R-E-P-E-L. Pass it off. Okay, Tiffany. A material that gives up or loses its electrons easily is called a good conductor. Pass it. A material that resists the flow of electricity. Insulator. Almost done here. 2 more questions. Good, Matt. For electricity to flow, you must have a complete path or... Oh, come on. A complete path for the flow of electrons is called a... We made them on the very first day. Oh, yeah. No man won't hear you if you whisper. Okay, I'll give you a half a squeak for that one, because you got help from your friends. Last question. Oh, come on. Bianca knows. Give it to Bianca. She wants it. She's confident.
Let Taylor do it.
All right, Taylor. What are the 3 particles in an atom?